So, hello everybody. This is Michael Riemer speaking, and I welcome you to today's seminar, the fifth in a seminar series. As you see here, a seminar series organized by HIWeather, and today the theme is on hazardous weather processes, with the subtitles Observations and Case Studies. So very briefly, for those of you, so this is our today's lineup. For those of you who have not yet attended to one of these seminars, the way you can interact with me as the host and my co-host Martin Wegmann and the speakers is through the chat. So you have the opportunity to ask questions through using the chat option. And the way we would like to do that is that you ask your questions as they come along during the presentation. After the presentation, we will have a look into the chat, or we'll monitor it during the presentation, and then we'll ask them in order. As an information to all of you, the presentation will be recorded. And in the very beginning, I would like you to just very briefly put your names, your affiliations into the chat, sort of using the Ask Chat option there. So you're not really asking a question, you're just introducing yourself, so we that have a bit of an overview who is attending the seminar. So one thing I would like to do first and foremost is to thank my co-host Martin Wegmann for the excellent organization of this seminar, the whole series actually. So he's covering the technical side of it and gives us great support in using all that. And without him, this seminar series would not have been possible. So as an overview, we have a total of 5 talks today, so I'll start with an overview, and then that also puts the four following presentations into context. The talks will be about 15 minutes long, and then we have 5 to 10 minutes of questions, depending on how the discussion is going. So at this point, let's see. Yeah, I would actually like to start showing you this agenda. So you can also see the faces of the presenters today. So this is me speaking, Michael Riemer. The first we'll do here is to do a bit of a presentation round of our presenters. So I'm an atmospheric dynamicist working in academia at the Johannes Gutenberg University in Mainz in Germany. I'm a steering group member of the HIWeather project. I'm coordinating there the predictability and processes theme. I'm also a steering group member of a large collaborative research center in Germany that is since recently a joint project of WWRP, which is called Waves to Weather, where we also address basic fundamental science questions about predictability and in different weather systems. So that'll be from my side. So we go through the presenters now in order of their appearance. So next will be Calvin Elkins, please.
All right, good morning. My name is Calvin Elkins. I am currently a PhD student at the University of Illinois at Urbana-Champaign in the United States. I am actually here in place of my advisor, Dr. Deanna Hintz. She had to be out, so what I'm presenting is my research, but it is under her. Under her, I'm researching severe weather, specifically hail in Argentina. We had a project called Relámpago that we did in 2018. So I'll be presenting some findings from there and some of the things that we're trying to look at having to do with social media as well as severe weather. Personally, I am interested in researching severe weather and understanding more how social science, social media, and things like that can improve weather warning processes. I am active duty in the United States Air Force right now, but this research has nothing to do with the Air Force part. This is solely for my education. So that's why I am here.
Thank you, Calvin. Next speaker, next in the list is Rob Rogers.
Good morning, good afternoon, good evening, everyone. My name is Robert Rogers. I work at the NOAA Hurricane Research Division, which is in Miami, Florida. My main areas of interest include aircraft observations, using those observations to better understand and predict tropical cyclone structure and intensity change processes. And so today, I'll be talking about how we do use those aircraft observations to make better predictions of tropical cyclones.
Okay, great. Thank you, Rob. The next one is Peter Knippertz.
Hello, everybody. My name is Peter Knippertz. I'm a professor of meteorology at the Karlsruhe Institute of Technology in Germany, and I'm one of the 3 speakers of Waves to Weather, the consortium that Michael mentioned earlier. And so my research interests are in the area of atmospheric dynamics, so the kind of physical mechanisms that drive weather systems. And we have a focus in my group on tropical weather systems, and more specifically on rainfall systems in Africa, in the African tropics. So that's what I'm going to present here today.
Okay. Thank you, Peter. Our last speaker, last but not least in the list, is Linus Magnusson.
Hi everyone, my name is Linus Magnusson. I'm working for European Centre for Medium Range Weather Forecast, ECMWF, based in Reading, UK, and I'm in the evaluation section. And one of the areas of interest when working in is severe weather evaluation. So that is what I'm going to cover in my talk later this afternoon.
Okay, great. Thank you for your brief introductions. Then I'll go ahead and start the presentations with my overview. Where did it go? With my overview. So is this being shared, Martin? Do you see my title slide? Yes. Okay. So as said, I'll present an overview very briefly of what high weather is, and then in particular what the predictability and processes team within high weather does and what the goals are of this theme. So as you may know, high weather is one of the 3 core projects of WWRP, which is the World Weather Research Program of the WMO. Research in high weather is organized into 5 different themes, and 4 of which have already presented a seminar here. And today it's the theme Predictability and Processes that is hosting this seminar. High weather has a mission, and that mission is to promote cooperative international research to achieve a dramatic increase in resilience to high impact weather, hence the name. So high weather stands for high impact weather. So it has a clear focus on that. And how do we attempt to do it? First, by improving forecasts for timescales of minutes to 2 weeks. So basically ranging from nowcasting to what is usually perceived as the limit of predictability of traditional weather forecasting. And second, and at least equally important, is by enhancing the communication and the utility of these forecasts for social, economic, and environmental applications. So Brian Golding, one of the co-chairs of high weather, has sort of come up with an illustrated schematic to illustrate the scope of high weather. So if we look maybe 100 years back, how would people make decisions in the face of severe weather coming up? So they would probably look at the sky, maybe see a storm coming, and then decide to seek shelter or to change the course of their ship. Nowadays, fortunately, we are in a more we have come a long way, and we are in a much better situation. We have quite some ability to forecast the weather, but not only the weather in sense of the atmospheric state, but also the hazards that may develop from that, say, flooding, and now also increasingly then the actual impact that this hazard will have, because not all hazards have the same impact all the time. So we come a long way in terms of forecasting, but then these forecast products may be fairly complex, and stakeholders may have specific needs. So to communicate the information from the forecasts, it's very helpful to have experts that give out warnings. And then the way the warning is phrased will actually have impacts on how decisions are being made. So this is what we call the warning value chain, because each of these mountains that you see here sort of, they add value to the chain of events that lead to a warning. The predictability and process theme is basically situated in the left-hand side of this value chain, basically in the traditional business of weather forecasting, using observations to improve forecasts, to improve process understanding that then would lead to improved forecasts, and also bridging over to forecasting hazards. So the goals, of course, are improving knowledge and understanding of the processes that underlie weather-related hazards, so as to assess their predictability, and then eventually improve forecasts, which are the meteorological source sort of for the warning value chain. High weather has, well, of course, a focus on high impact weather, but they're a focus on specific hazards, and it's a broad range of hazards that you can see here. So it ranges from urban flood, urban heat and air pollution, to wildfires, extreme local wind, and disruptive winter weathers. So with that, I now come to our predictability and processes theme, and here, in the briefness of time, I just can give you sort of flavors of what we do there. So on the one hand, we do study predictability of mostly individual cases, for example, using operational ensemble forecast systems. So this example here is from a windstorm that affected Northern Europe in 2015. The blue box and whiskers that you see on that plot basically give you the ensemble forecast distribution of 24-hour wind gusts. The initialization time sort of goes from left to right. So to the right, the forecasts are initialized closer to the actual event, and the event verifies with that star in the right-hand upper corner. And the red box and whiskers, they are climatological distribution of the gust forecast. So how we can interpret that is basically the ensemble system definitely gave us a heads up on this event. If you look at the initialization times closely, maybe something like a week ahead of the event. Another result here would be that the ensemble underestimated, at least in a not post-processed way, the magnitude of the event. So this is basically diagnosing the predictability characteristics in operational models. You could go for individual cases a step further and not only look at the predictability characteristics, but also try to link them with the dynamics, at least as seen by the forecast model. So this is again an example using the operational ECMWF ensemble forecast system. The sort of ensemble distributions are given in the lower panels, where the height. So this is for the tropical transition case, so a hurricane formation by a specific pathway of Hurricane Chris in 2012. So the height of the bars in the lower panel show you the number of ensemble members that form any cyclone, and the colors then denote whether it's sort of a cold core cyclone, so whether the forecast system thinks this one will be an extratropical storm, or whether it goes tropical, which is then the red, the warm core systems. And then in this study, we try to link these ensemble statistics with say how well precursors of the system were represented in the model using basically ensemble sensitivity methods. Another line of work would look at, say, parameter sensitivities in numerical weather prediction models. So this is a study that did a comprehensive sweep of the phase space of uncertain parameters, not only so for microphysics, that is, but not only the microphysics uncertainty, but also how that uncertainty relates to uncertainty in the environment. And I think that's an important thing to do. If we talk about sensitivities, then we should all first look at the most important sensitivities. And so this is actually a study for an idealized case. And I don't want to go much into details here, but we could see, so this is for precipitation characteristics, and the bars on the right-hand side, they show us how sensitive production of hail basically is, and there we do see fairly significant dependencies on how exactly cloud condensation nuclei or ice nucleation particles would be represented. But said again, that's only for one idealized case, and specifically for a convective cell that is initiated by a cold pool. If you look at other initiation mechanisms, the sensitivities could look slightly differently, and if you use another ice microphysics theme, then your sensitivities may look quite different. So this is basically predictability studies in a case study framework. The second flavor sort of that we have in the task team is that of field campaigns. So HIWeather does not conduct the campaigns themselves, but we have representatives of these campaigns, and of course the campaigns provide crucial observations for process understanding. And or we take, and so if the campaigns are still in the planning phases, ideas of HIWeather are taken into account into the planning, or at least considered in the planning phase. And so you might see that the ranges here are also very strong range from geographically from the North Atlantic to South China to Argentina, and process-wise going from severe precipitation to boundary layer variability that is important for convective initiation. So there's actually quite a challenge here, and that is the broad scope and the fragmented communities that need to come together to work on these topics. So that's actually something that the implementation plan had realized of HIWeather for the project in general, but it's particularly true also for the predictability in processes theme. So the very diverse set of weather of the focal hazards are related to very different weather systems, and our sort of the atmospheric dynamics predictability community tends to cluster around specific weather systems. So it's hard to integrate work based on these focal hazards. The same is sort of true for the multitude of the relevant processes. So usually communities revolve around, say, the microphysics, so that the cloud community is a big one, and then we have turbulence communities. Now maybe I'm also considering the urban canopy here, and I didn't even mention atmospheric dynamics here, which is again a different community. And scales are vastly different too, so it's hard to integrate based on these more common ways to forge collaborations. And what is important for me here to mention is that if we want to understand the weather system that lead to high impact events, we may not only study the high impact events, but we need to understand the governance processes of the regular events too, so that we have the opportunity to actually compare and then understand what makes it high impact or what makes it particularly severe. So there is a lot of expertise that we bring together here in that theme, but the question is how to synthesize and how can we make form something that is bigger than the sum of its parts, basically. So there is hopefully a way forward, and this is through key activities that HIWeather has recently started. And if you're familiar with the HIWeather Workshop, it's 3 activities that actually form the content of the workshop that will start next week. So it's basically successful citizen science, a warnings value chain, and something called towards the perfect warning. And I'll talk a little bit about what it is in a second. So the workshop on successful citizen science, it's a broad theme that encompasses the full value chain, but it does include also the use of what people tend to call unconventional observations, sort of everything that is low quality because it comes from low cost sensors, for example, mobile or in mobile sensors or windshield sensors in automotives, or from social media. But the good thing is there's a lot of that. So there's a lot of data, though low cost. There should be some value in actually using it, and Calvin Elkin's talk is in that context, as he's using social media data to identify hail-producing storms. Then the second key activity is, its full name is actually the end-to-end evaluation of the value chain. So I've introduced the idea of the value chain earlier, but this chain has not been evaluated end to end, in the sense that it's not well known how well the flow of information is, at which part of the value chain most of the information is lost, how for uncertainty, for example, is treated, uncertainty information is treated. So this will be one of the key activities, and in doing so, or as part of this activity, a catalog will be compiled that encompasses lots of cases, so metadata for these cases, and my hope is that people would use this catalog and this assembly of many cases to try to do, say, meta studies, to learn something that goes beyond individual or just a few case studies. And Linus Magnussen's talk is in the context of this key activity. And finally, there's a book being written with the name Towards the Perfect Warning Chain, and the main theme of this book are partnerships to bridge the gaps. So those of you who have seen the value chain schematic a few times maybe have been asking themselves, where are the bridges? There they are. So the idea is that the mountains, this is expertise that sits in specific communities or maybe in specific agencies and institutional bodies. And when these communities, institutional bodies need to communicate, there may be some friction, there may be a way. So information may be leak out during passing from one mountain to the other. And the partnerships present the bridges that should help to lose as few information as possible. And here in our context today, Rob and Peter will talk mostly about observations and how process understanding or predictions can be improved. And with this, sort of with this lineup that also serves as the list of the following talks, I'll be ready to take questions and comments.
So far, no real questions for you, Michael, but maybe our speakers have questions.
Okay, so if this is not the case, we will move on and take it to our first real speaker, to our real first presentation, which is an afternoon in this afternoon here in Germany, at least, which will be by by Calvin Elkins. Please go ahead, Calvin.
Oh, okay, I'm just gonna get everything shared here. All right. Sorry, just want to make sure everything's working properly. All right, hoping everything works. I'm getting a bad network quality, but if you can see, I can continue. Sorry about that. Good morning, everybody. Again, my name is Calvin Elkins, PhD student at the University of Illinois at Urbana-Champaign. I'm also active duty United States Air Force, so I am here through the Civilian Institutions Program at the Air Force Institute of Technology. But as I said before, this talk will have to do with my PhD research only. My advisor is Deanna Hintz. She wasn't able to present today, but she is there in the chat, so hi, Deanna. I also saw Paula Salio from Argentina, who was also very integral in the things I'm going to talk about here today. So what I am doing, using social media to identify hail-producing storms in Argentina during the 2018-2019 severe weather season. So this is actually going to be in two parts. One part's really going to speak to using the social media, and the other part is going to speak to how we're using radar to really look at these storms and identify these storms as we move forward. So why Argentina? Well, near the Sierras de Cordoba, there are very deep and intense thunderstorms, and these thunderstorms have proven to be some of the most active hail producers in the world. So this presents the challenge of how to better predict the onset of these hailstorms. Some of the challenges being there's a variety of storm structures. So there's a need for forecasters to understand storm types and severity. And in this part of the world, there have been a lack of hail-focused studies specifically using ground-based radar. So that gives us something to look into and use. Just looking as far as radar. We did the Relámpago project in November and December 2018. I was able to go down there. We were centered in Villa Carlos Paz, Cordoba, Argentina. As we said, that region is prone to extreme weather, the large hail, quick upscale growth of mesoscale systems, and an urban flood threat. Now, at the time, you see the circles to the right on those cities in Argentina. At the time we were there, there were 5 active radars that were being used. I believe more have been added since. I'm sure Paula can testify to what's operational now, but at the time, that's what we had to work with. So looking at the limitations of the time and looking to see how we can better improve things, well, we thought about social media data. Twitter, because it's very temporal, people tweet things as they see it. There are a lot of users who tweet statements and pictures and videos of hailfall. SMN, which is Argentina's weather service, they'll send tweets with their alertas and weather info. There's also bots that will retweet and send retweet with severe weather hashtags. And there are also like special weather interest groups. They will also amplify the message. So there's a lot of weather information that can get out there during times of severe weather. We also discovered that other social media platforms, things like Facebook, aren't as useful in real time. So here we're going to stick more to Twitter data. And the question is, can this data be used to identify these hail-producing storms? And also, can it be used to improve nowcasting and storm verification? So getting to the social media data, this brings the research question of just how useful is this data? How much data moves through Twitter on a hail day? What is the signal to noise ratio? How do you separate useful data from non-useful data? And is it even necessary to do that separation? So if you look down here, the question is, what fraction of incoming Twitter data is useful versus noise? Well, we have to define useful. So defining useful as a tweet that is within spatial and temporal bounds where a forecaster can use the data to amend forecasts, issue or extend warnings, or verify hailfall. This is going to depend on the timing and location of the tweet with respect to the position of the storm. Noise is going to be any tweets with hashtags, images, etc. that are related to the event but can't be used for nowcasting or verification. And then later on, we're going to have to define what kind of tweets would be considered noise. Now, looking at the radar and identification process of these storms, the question is what storm mode, what shape that it takes on radar and underlying characteristics are most likely to produce hail in the Cordoba region. Remember on the first slide, we said there's a variety of storm modes that move through. So the working hypothesis is that supercells, which are individual rotating large storms, are the most prolific hail producers in the Cordoba region, and that non-supercell cellular convection or individual storms that don't have the same kind of structure and rotation will produce the second most. It's important to note that this work does not take hail size into consideration because a lot of studies do. A lot of studies will look at large hail or small hail. This one is simply looking at hailfall in total. Quickly looking at our classification modes for those who might not be familiar. Multi-cell unorganized means there's a lot of cells there, but they don't have a real strong organization. Multi-cell organized means that you have a variety of cells in an area, but they're kind of interacting with each other. Sometimes they're connected and will be a very broad region. A discrete non-supercell is a discrete cell all by itself, but it's not showing the rotation that we like to see with a supercell. And then discrete supercells where you have clear rotation, it's one storm by itself, and it'll often show that little hook. If you look down in the bottom right, you can see that little hook appendage on the north side. For anybody in America or Canada, in the Southern Hemisphere, supercells will actually look flipped to you. So that's what you're seeing. Now getting to the social media, we had to gather this data. So how we identified the storms to look at, we actually used the social media first. We had storm reports through earlier research through the HINTS research group and Jake Mulholland, who came up with that classification scheme here at the University of Illinois. We also have something called Brandwatch, which scours social media for certain hashtags, so we were able to get reports from there. And we also have the ground reports from Relámpago and from our partners in Argentina. Now, not all of those data were from Twitter, but we have those data that we can use to verify what we were seeing with the social media. We created the database looking for initiation time and location as determined by the first radar cell that we saw at 35 dBz, indicating some moderate convection. Taking note of the hail time and location, looking for that first sign of hail being dual pole signatures or a 3-body scatter spike on radar. And then we determined the convective mode, which were the 4 modes that I showed just before. Determine the convective mode of the storm at the time of the hail. And all the radar data we used came from the Cordoba radar, which we call RMA1. With these data sets to identify the possible hail cases, what we needed was a tweet that showed photo or video. That way we could be more confident that what we're looking at was actually video. Sometimes you do have to be careful. There was one kind of humorous thing where somebody took, and I'm not kidding, they took ice out of their freezer, held it in their hand and said, "Ooh, look, severe hail." So you do have to go through and pay attention to what people are doing there. After you do that, we interrogate the radar data for the individually identified storm days. And you're looking for certain things. Are there other cells that move over the area? Do you see a clear 3-body scatter spike that indicates there is hail there? If you don't see that, but you have the report on the ground, is there something in the characteristics of the radar that lets you know that there is a high likelihood of hail there? Once we can verify all that and that target cell is identified, we can assign the storm mode classification. We can use radar data to track the cell to its origin, measure the time from its origin to the first time of hail, and measure the time and location of that spot with respect to the tweet identifying it. So this brings us to the statistics. From our research, we identified 165 data points from 141 storms. Now, when we go just to the tweets, we had 47 tweets from 37 storms. The helpful arrow right here pointing you to the 37 data points that we had for those storms. Now, some storms have multiple reports. That's why the numbers don't match. In that case, we only looked at the first report of the storm. This data here, the x-axis is distance at closest approach to the tweet location. So the closest that the cell moved to the city that the tweet said it was from. And on the y-axis, that's the time. That's the number of minutes between the closest approach of the storm and the time of the tweet. So that should always be greater than 0 because nobody should be tweeting about a storm that hasn't approached them yet, ideally. Some of the things to note here. Number one, location accuracy is very good. Some of the things that sometimes you'll worry about when doing something like this is population bias. Cordoba being the bigger city around there, you might think that you'd have a lot more reports there, but a lot of the smaller cities actually had these reports. So you didn't have a lot of population bias, and most of the storm reports were within 10 kilometers of the location of where the tweet came out, which is very good. One of the issues is there's a wider spread as far as time goes. Only 10 of these 37 got tweeted within 30 minutes of the storm. And these storms tend to move pretty fast, so that's kind of important to know. If we expand it to 60 minutes, it's still only 18 of those 37 that are still getting tweets of the storm within an hour of it passing. So as we move forward, that's something to think about. And then here, there's actually not a lot of outliers. There aren't a lot of outliers as far as distance or time once you get past 2.5 hours, but 2.5 hours can be very important there. But it is interesting that there aren't too many of these data points that are far outside of the range. Now, looking back at the storm mode, the storm type, to see which ones happen most often, we found out that it's actually discrete non-supercell that was overwhelmingly the top hail producing mode. Now that could be due to the volume of the updrafts, very broad storms having large updrafts. It's also that some discrete non-supercells could be discrete supercells that are actually hard to identify on radar. There wasn't a significant difference in numerical distribution between the other 3 types as compared to discrete non-supercells, and also not a difference in distribution from early to late season. As you see here, separated October, November, December from January, February, March, and a lot of the percentages stayed pretty much the same. So that seemed to be pretty even across the entire season. But there was a significant seasonal difference in time from initiation to hail. If you look in January, February, March, with the exception of multi-cell unorganized, all of the times from initiation of storm to hailfall is much shorter in January, February, March compared to October, November, December. This data could indicate that there are fewer but more intense storms in January, February, March. But I do have down at the bottom, there's a note that Relambago ran in October, November, December, and you have a lot of researchers down there. There's a possibility that we could have detected more because you had more instruments looking, and that might contribute to the difference in the number. Because of that, in the future, we might want to look at something like 2019, 2020 and see if we see the same thing. This is 1 year of data. You can draw some hypotheses from it, but you're going to want to look at other years and see if all of those patterns do stick. So our main takeaways: discrete non-supercells being the most prolific hail producers with the highest number of hail producing systems and the shortest time from initiation to hailfall. The only difference that we saw in early to late season was initiation to hailfall time. Now coming back to social media, what fraction of that incoming Twitter data is useful versus noise? Well, what we were able to learn here was that spatially, the tweets tend to show very good correlation with the location of storms. So you don't have a big problem spatially. What we are going to have to be careful of is that temporally, there's a lot of variance. You're not getting a lot within 30 minutes or an hour. Again, fewer than half of those cases were within 60 minutes. And in this case, noise was already filtered out, so we're not even addressing that. So the new question this brings up is, what combinations of distance and time will be the most useful for forecasters? And a question that I came up with discussing with my advisor is, will that time matter if we can still see the cell on radar? In other words, if we get a report that there's hail from this cell and we can see it on radar, does it matter how late that tweet comes in if that cell is still alive? That's something that we can discuss at a later date, future work. Tracking these storm paths from initiation to hailfall, because storm paths, where they initiate, how they travel, may be important to the mode and the timing. Analyzing how storms initiate. Do they initiate on the mountains? Do they initiate out over flatlands? Do they initiate in the area of other convection? And the main challenge, not to forget, is how to use all of this data to improve prediction. One of the things that we thought about was replicating a real-time Twitter stream for a hail event, taking an event that we didn't cover that has a lot of tweets and kind of simulating how we would go through and use this data to look at our hypothesis. Do the tweets need to be filtered? What distance time combos will be the most useful? And taking that data to create some kind of decision tree or a nowcasting method that could help with weather warnings, extending warnings, and pretty much coming up with a way to make this real-time social media data useful in this environment. And that gets to signal to noise ratio. What different categories to place tweets in. You have bots, you have retweets, you have news, official orgs, silly and irrelevant posts. How do we deal with those? Do we have to deal with those? Are they easy to filter out? So everything that's been presented here is preliminary data. Like I said, this is part of my PhD work. So in the future, we'll get some of the answers to these questions and see how they work out. This is thanks to everybody who's worked with me here at the University of Illinois, our partners in Argentina at SMN and Universidad de Buenos Aires, everybody who worked on Relámpago, and of course the Air Force Institute of Technology, which is why I'm here getting my PhD. That is all for me. I guess I can stop screen sharing. Oh, sharing is paused.
Okay, Calvin, thank you very much for a very interesting talk. We have a bit, unfortunately, we have a bit of a technical issue here that will not affect the questions that you will get. It only affects me because I cannot see the question. I can't see the questions. So Martin is going to moderate the questions and read them out to you. Yeah, my apologies that I would have loved to do that, but for some reason I'm not able to see the questions. Martin, please go ahead.
Okay, so we have two questions right now. So Paul Joe wants to know, for report time, I would have thought that those social reports with images would be very close in time to the phenomena. Do you have any speculation about why the 30 minutes delay?
Yeah, my speculation off the top is that some people might take a picture or record it and for whatever reason just not upload it immediately. We have hail here sometimes in Champaign, and I try to record it and send it out immediately, but that's also how I'm thinking about it. I'm a severe weather meteorologist. I know what National Weather Service forecasters can use, so I try to get that to them in a timely manner. Perhaps your everyday person thinks it looks cool. They make a recording of it, and maybe it's not as important to them to get it out in a timely fashion. They're not a meteorologist. This is just something kind of cool that happens.
Right. So Michelle Spruce from Exeter wants to know, regarding collecting the Twitter data, which hashtags or other terms within the tweets did you use to determine it was a hail tweet?
So look for something having to do with hail. So Granzino, Paula, correct me if I'm saying this wrong, but Granzino is the Spanish word for hail. Somebody who speaks Spanish can type that in properly in the chat. But also things that were like stone or pebble in Spanish. Again, I don't want to say it wrong. Then looking for hashtags for the names of all the little cities in the area. So it was combining some hashtag about hail or hailstone with a hashtag for the city or the area, and making sure that only looking at tweets that are actually coming out of Argentina to kind of to filter it. That worked pretty well. There were only a few days that we had to go back and do a really deep sweep and discover that we missed. There's actually I have a very, very long line of hashtags, and Deanna and our other researcher Rebecca can attest to that. We have a very long list.
Right. A lot of questions coming in. Maybe one or two more. Maybe that connects also to a question that I have. Ron McTaggart Cohen, I hope I don't butcher that name. Could you design a social media campaign that would serve as training so that folks would know that tweeting quickly is important? And my question would be like, what would be the perfect tweet for you to get the most information out of this? So maybe, you know, like having the perfect hashtag, the perfect photo, the perfect location enabled. Is there something like I don't know, a prototype format that people should tweet?
To answer that question, there actually, I believe it was in Switzerland, they actually did a campaign where, I believe it was the Swiss Weather Service, they actually put out an app and ran a campaign telling people to actually tweet their weather, not tweet, I'm sorry, it was their own app, but use this app to report weather. That way they could get all the data in and kind of use that as crowdsourcing. It's probably possible down there. I was only in Argentina for so long, so this probably goes something like Paolo or people at University of Buenos Aires, but I'm sure that there could be a type of campaign to do that down there. As far as the perfect tweet, the hailstone, something to compare the size to, and tweet it within 5-10 minutes as soon as it comes. That is actually something when we were at Relámpago, we gave people little rulers so they could actually measure the hail and kind of encourage them to do things like that. But yes, timely and with something that can actually measure the size of the hail. And in cases where there is a lot of hailfall, maybe a short video showing what kind of hailfall we're looking at.
Right. Okay. So there's more questions in the chat. Magnus also made a comment about the weather app. I know that Meteo Swiss has functionality like that for hail. So maybe you can reply to the other questions in chat and we move on with the next talk.
Okay.
Thank you so much.
No problem.
Perfect, Martin. Thank you for moderating the questions, and moving on to the next talk. Rob Rogers, please take it away.
Okay. Good morning, good afternoon, and good evening, everyone. Let me share my screen real quick. And let me just move it so I can get to it. Can everyone see my screen?
Yeah, you're good.
Great. Okay, so thank you again for allowing me to speak to you all today. My name is Rob Rogers. I work at the NOAA Hurricane Research Division, which is in Miami, Florida. And what I'm going to talk about today are ways that we can use observations, in particular aircraft observations, to improve our understanding and prediction of tropical cyclones. So this picture you see here is an actual picture within a Category 5 hurricane eye from one of the aircraft that we fly on. So I want to talk to you a little bit today about how we can use that data to make better forecasts ultimately. Let me see if I can advance. Is there a lag here? There we go. So the real challenge or one of the big challenges, at least with tropical cyclone forecasting, is the intensity forecasts. So if you go back and you look at the National Hurricane Center's forecast errors at the 48-hour lead time back to 1994, so about 25 years ago or so, and you set that value to a value of 100, and then you look at how the track forecast error, at least, has improved over the past 25 years or so, you can see that our track forecast errors have been reduced by about 70%. However, if you look at the intensity forecast errors, that's the red line, you can see intensity forecast errors have reduced by only about 30%. So about half of the, or less than half actually, of the error reduction that we see for track forecasts. So, obviously there's an issue in terms of our intensity forecasts. They really have lagged our track forecast improvements. So one question becomes, how can our observations that we collect through the work that we do at HRD, how can those observations be used to make better TC intensity forecasts? So we have put together an experiment that's actually been on the books for about 15 years now. It's called the Intensity Forecasting Experiment. And so there's actually been a couple papers that have come out in the Bulletin of the American Meteorological Society, one in 2006 and another one in 2013. And then there's another one that we're actually in the process of just about finishing up and submitting, and hopefully we'll get that published in 2021. But IFEX is intended to improve our prediction of tropical cyclone intensity change by addressing three primary goals. The first goal can be considered as directly trying to improve forecasts. And in terms of the observational side of that, that involves collecting observations that span the tropical cyclone life cycle across scales. So, intensity change processes span scales from the environmental scale, thousands of kilometers, down to vortex scale, maybe 100 kilometers, convective scale, 1 kilometer, let's say, and then turbulence scale and even microphysical scale. So to the extent that we can capture these with observations, we want to collect them across the life cycle, and that will go toward better model initialization as well as model evaluation. The next primary goal is what I'd call nowcasts. So that involves developing and refining measurement technologies that can provide an improved real-time monitoring of tropical cyclone intensity, structure, and its environment. And finally, the last goal I would call research or processes, really trying to get more of the fundamental physical processes and improving our understanding of those processes. In particular, those processes that we think are important in intensity change. And not just for hurricanes, not at the mature stage of a tropical cyclone's life cycle, but in particular earlier in their life cycle, whether it's a tropical storm or tropical depression or even a pre-depression. So these three goals, forecasts, nowcasts, and processes, really form the core of what IFEX does. They really provide a linkage between the observations and the modeling, the data assimilation, and the theory that form the foundation of the work that we do at HRD and within NOAA as a whole, and also within really the broader tropical cyclone community, I'd say. So what are some of the primary observational technologies that we have as part of IFEX? Well, the main platforms are, they're airborne platforms that we focus on. And so the aircraft that we use are, you see the two pictures on the left here. So we have two NOAA P3 aircraft. So those are the aircraft that punch right through the eye wall of a hurricane. That picture that I showed you at the beginning was taken from a P3. So we have two of those, and then we also have a high altitude jet called the NOAA G4. So that flies at about 41 to 43,000 feet, so about 12 to 14 kilometers or so altitude. And that primarily samples in the environment around the storm, around the tropical cyclone, but it has from time to time actually been known to overfly the inner core of the tropical cyclone. NOAA is actually also in the process of acquiring a new high altitude jet, a G550, which will have actually an even higher altitude, higher ceiling, and a longer duration and range. So we hope to get that online in the next few years or so. In terms of the actual measurements, well, we have the in situ measurements that we have from the aircraft, in particular the P3s. That includes, of course, the winds and the pressure and the temperature and moisture measurements. We also have expendables that we release from the aircraft, so they're drops-ons. These are instruments that actually fall to the ground with the parachute, and as they're falling, they measure temperature, pressure, winds, and moisture, and report that back to the plane, which we report back to the ground. We also have buoys and other types of expendables that measure ocean conditions, sea surface temperature, as well as subsurface temperature, currents, and salinity, and so forth. We also have remote sensors on the aircraft. So we have a tail Doppler radar. So you can see these antennae on the backs of the P3s, at least, the little cones that jut out from the back. Those are antennas that actually allow us to get measures of not just the reflectivity, but also the three-dimensional velocity. We also have instruments that measure the surface wind speed, the SFMR and HIRAD. And so these are basically instruments that measure the brightness of the ocean. And from that, we can infer what the wind speeds are at the surface right underneath the aircraft. We have instruments that measure the wave field, the WSRA. So that tells us, what the waves look like under the aircraft, which is very important, of course, for shipping interests. Scatterometers and profilers, which will allow us to get integrated measurements underneath the aircraft, as well as estimates of the surface wind and direction. And then finally, UAS, or unmanned aerial systems. And so these pictures in the middle, you see a NASA Global Hawk, and you see what's called a Coyote UAS. These are examples of some of the unmanned systems that we either have or we partner with NASA on. And then the G4 tail Doppler radar you see in the middle there, that's a TDR that we actually put on the G4 aircraft. So now we've got Doppler radars on both P3s as well as the G4. Some of the newer instrumentation I won't have time to get into today include the Doppler wind LiDAR in the bottom right corner. So those are just ways that we can get measures of winds, wind direction and speed in areas where the tail Doppler radar cannot measure. In the absence of scatterers, basically, that the LiDAR can give us some of those measurements. So it's a nice complement to fill in those gaps. So Mikhail did a really nice job at giving an overview of the value chain, and I just kind of wanted to talk about where I think IFEX fits into this warning value chain. So I put up here a picture. I think this is a slightly older image of the value chain from a paper that Brian Golding published last year. But in particular, I want to talk about where tropical cyclones I think would fit into this value chain. So here are the peaks that Mikhail talked about. These are, I guess, what Brian calls the peaks of expertise, and then the valleys of death, so to speak, and then the bridges of communication across these various valleys. And so in terms of the tropical cyclones, the primary observations that we have that we use as part of the value chain include, of course, satellites, as well as surface observations, and then aircraft data. And then the main parameters that we try to better predict with the numerical models in terms of tropical cyclones include the minimum pressure, as well as the position of the storm and the peak winds. And so IFEX, of course, really falls on the left side of this value chain. In particular, IFEX provides the aircraft observations to improve our model forecasts of key TC parameters such as pressure and winds and position. So now I'm going to give some examples of how we're working toward addressing each of these IFEX goals. So the first goal I'll talk about are ways that we're improving the forecasts. So, one of the key observations that we use in our assimilation within numerical models are dropsondes. And so there's been a problem though, when you release dropsondes in a high wind environment like a tropical cyclone, they often will, they'll of course drift with the wind. And so if you release a dropsonde, for example, near the eye wall, it can go a significant distance around the storm as it's falling toward the surface. And so this image on the left is showing an actual location where we released a dropsonde from a P3 aircraft, and then where that dropsonde moved after we released it. However, if you look at where in an older formulation, the global or the numerical models assumed a specific single location of where that drop was occurring, when in reality, of course, the drop was really moving a significant distance in the horizontal. That can have significant implications in terms of the assimilation of winds, for example, and can really give you an erroneous initialization. In the case that I'm showing you here, the dropsonde drifted by 15 kilometers, but there are easily cases where drops can drift completely around a storm, or halfway around the storm if it's in a particularly strong eye wall. So we actually implemented, and working with the Environmental Modeling Center within NOAA, we implemented a technique where we accounted for the drift of the dropsondes, and then we ran a series of evaluations and verifications to see how that improved the forecast. And in fact, we did see that when you account for the dropsonde drift, that's the red line here on the right panel, you can see a reduction in the intensity forecast errors just by accounting for those drifts. Another example of how we use the observations to improve our forecasts is in model evaluation. So one of the key processes that really plays a role in determining a tropical cyclone intensity is the boundary layer. Of course, the boundary layer modulates or governs the fluxes of moisture and temperature, as well as momentum with exchanges with the sea surface. And so the left panel is showing you observations from thousands of dropsondes released in many different tropical cyclones, composited in a composite framework. So the x-axis is showing you a normalized radius, basically normalized by the radius of maximum wind. So value of 1 means right at the RMW, or radius of maximum wind. And so this is going out to 3 times the RMW. So using a composite of these dropsonde observations, we get a sense as to how strong a typical inflow is. This is radial flow, so showing flow toward or away from the center of the tropical cyclone. So in the lowest 500 meters to 1 kilometer, the boundary layer is of course governed or dominated by inflow. And you can see the strongest inflow is really concentrated at about 100 meters or so. But you do have inflow that extends over about a depth of about 500 meters to over 1 kilometer. So compare that now with a formulation of inflow with a sort of our state-of-the-art numerical model at the time, HWRF, operational numerical model at least. There's a formulation of eddy diffusivity, or mixing in the vertical, that the model used, and it was basically based on an old formulation from the GFS, I believe it was, and it essentially had mixing that was much too strong. And so when you use this value of eddy diffusivity that was much too strong, and you looked at what that composite type of inflow structure looked like, you can see the inflow layer, is depicted by this black solid line, was quite a bit deeper, and the magnitude of the inflow was quite a bit weaker than what we get from the observations. So that pointed to a clear bias in the structure of the boundary layer when you use this incorrect version of the eddy diffusivity, or the mixing. Now, using aircraft observations, flight level observations, we were able to get a better estimate of what the actual mixing should be. And when we corrected for that mixing and then ran it again in that HWRF model, we can see a much more consistent inflow depth as well as inflow strength when compared to the observations. So clearly a much better structure in terms of the inflow in the boundary layer when we use those corrected eddy diffusivities. What impact does that have on the actual forecast? So we ran a set of cases where we used this corrected KM, or corrected eddy diffusivity, for 2 specific tropical cyclones that underwent rapid intensification. So the top 2 lines, the solid lines, are showing you the overall error, and then the dashed lines, the red and black, are showing you the biases for both the corrected KM values in red and the incorrect in black. And so you can see that when you use the corrected KM, the intensity errors are reduced out, across all lead times, basically out to 4 to 5 days, and the biases are also reduced. So, at least for these 2 cases, using these corrected eddy diffusivities resulted in an improved intensity forecast, and even for cases that underwent rapid intensification. So, what's been the net result in terms of the skill of the predictions, both from a numerical modeling perspective and also just from an overall sense as far as what the observations, how they impacted the model forecasts. So what I'm showing you here are the changes in the skill of the HWRF model for 3 different versions. So a version from about 10 years ago, a version from about 5 years ago, and then a version from about 2 years ago. So this is across all lead times. So this is just a skill relative to a baseline value. So positive values indicate improved skill. And so the earlier version from about 10 years ago, you can see that there was some skill from using the HWRF model over a baseline out to about 36 hours, a little bit of skill, but then we actually had a degradation in our forecasts beyond that lead time. But now look at the version of HWRF from about 5 years ago. Now you can see an improvement in terms of the skill out to about 3 days. But you still see that drop off at 4 to 5 days. And then look at the most recent version of HWRF, or at least the one from a couple years ago. Now you can see a pretty significant skill in using HWRF across all lead times. So it's really been a substantial improvement, I would say, over the past 9 to 10 years. Now this is overall, this includes a multitude of changes to the model, including resolution changes and physical parameterization improvements and so forth. But if you just try to isolate the impact of the aircraft data only, so this is using the more recent version of the HWRF model. This is a similar type of skill plot that I'm showing you now, but the black line is just showing you the change in the skill when you actually incorporate aircraft observations versus if you did not include any aircraft observations. And even in that case, you can see an improvement of between 10 to 15%, about 10% or so, let's say, depending on lead time, at least out to about 4 days or so. So it's clearly indicating that just using the aircraft observations only, we're still getting an improvement in our intensity forecasts. So now let's look at nowcasts. Through a lot of research that we've done and others in the community, one of the things that we find is that the degree to which a vortex is aligned, it's vertically stacked, gives you a sense as to what the chances are that that storm is going to intensify. So if you have a vortex with a kind of a displaced or a tilted center with height, then it's less likely to develop, at least in the near term. So here's one example from a case of Hurricane Humberto from 2019. So these are winds that are actually derived from the airborne Doppler radar at 2 different altitudes. So the left panel is showing you the winds at the 2-kilometer altitude, and the star is showing you the location of the low-level center. And then the winds at 5-kilometer altitude, you can see an X showing you the location of what I call a mid-level center. And so you can see that they're displaced. The mid-level center is displaced a little bit to the northeast of the low-level center. This information is available now in real time for the Hurricane Center, and they've actually used that information in their real-time forecast discussions. Just one example, based on this data, they said, the Hurricane Center said in their discussion, the storm is still feeling some effects of southwesterly shear and dry air, which is causing a strong tilt in the aircraft data. Conditions are expected to gradually become more conducive for strengthening. But so again, this is a nice example of how the data that we're collecting is being transmitted to the ground in real time and being looked at by the specialists in terms of in helping them to make short-term intensity forecasts. This is a great example also of how they've really taken to this idea of being able to look at the Doppler radar data in real time. So this is a graphic that the Hurricane Center actually generated, and this is what the specialists can see in real time. This is showing you a swath of winds from a tropical cyclone Laura. I believe it might have been a tropical storm at this time, this year as it was approaching Cuba. So these are slices at different levels of the atmosphere, stepping up basically at every 500 meters, going from about 500 meters up to, I think, about 8 kilometers or so. And so the specialists have marked this red dot rather is the location that they flagged as the storm center. And so as you can see, as you step up through altitude for this particular swath from this pass of the aircraft through the center, you can see that that storm center again is not aligned. It's moving basically off toward the southeast. So that would suggest, at least for the short term, that the storm is not likely to intensify. However, if you look about 2.5 hours later, about 2 hours later or so, that same aircraft mission, now on the right panel, you can see that the storm center, as you step through height, it is much better aligned. There's not much of a displacement of that center as you go higher in the atmosphere. So that indicates that the storm is probably more likely to undergo intensification, in particular as it moves off the coast of Cuba back over the waters of the Gulf of Mexico. And in fact, that is what we saw with Laura. So again, this is a nice example of how the specialists are really looking at our data in real time and using that to help in their forecasts. Other types of technology, so newer technologies that we use. I showed an example of the Coyote unmanned system. So this is just a picture of how big the Coyote is. You can see it's really not that big, like a person can hold it easily. And so this is one of our scientists standing in front of the P3 aircraft. The Coyote is actually launched from the P3. So the P3 will go into the center of the storm or somewhere in the hurricane environment and release the Coyote through the dropsonde chute. So it's kind of like a dropsonde that you can pilot. And the great thing about the Coyote is that it is, of course, capable, since it's an unmanned system, it's capable of sampling conditions that any manned aircraft can really not safely go. For example, right near the surface in tropical cyclone environments. And so with that capability, something like a Coyote is really useful both for real-time monitoring of surface conditions as well as research, in particular air-sea exchange processes is another really nice application of this instrument. So this is just one example of the Coyote. It was actually released in several Coyotes actually were released in Hurricane Maria from 2017. So this is showing an image of reflectivity from the NOAA, the lower fuselage radar on the P3. So you can see the eye of the storm here in the eye wall. And so the Coyote was actually released in the eye of the storm where it says start. That white line there shows you the trajectory that the Coyote took after it was released and as it descended to the ocean surface. It actually got into the eye wall on the east side. So the right panel here now is showing you a time series basically of wind speeds from all the Coyotes that have been launched over the years. We've only had 7, I think, at this point. But again, you can see, starting from about 1.5 kilometer altitude, kind of a stair-stepped type of descent patterns, the Coyotes are measuring winds getting up to, 70, even 80 meters per second as they ultimately descend down and splash into the ocean. So these are crucial measurements that we can take right at the surface to really get a sense as to what the temperature and moisture fields and the wind fields look like in that really unsafe environment. So now the final goal I want to talk about are processes. So some of the fundamental research that looks at key processes. So this is a research result that I published a few years back where I took tail Doppler radar data from many different storms. So this is a composite type of analysis. And I looked at storms that were intensifying and looked at the Doppler data in those cases, and then storms that were remaining steady state. And I compared the structures of both the vortex as well as the convective structures and the distributions. So this is just one nice schematic showing some of the differences that we saw. So again, this is looking at things in a normalized radius framework, so normalized by the radius of maximum wind. So the dashed line here in the vertical is the RMW, the radius of maximum winds. This is a radius height plot up to 14-kilometer altitude. The shading is showing you the vorticity, or kind of the spin and the structure of the storm, both in the inner core and outside the RMW. And then the bars, the black bars, are showing you the locations of strong thunderstorms. We call them convective bursts. And so, you know, we can flag where these storms are located in a radial sense for both intensifying cases as well as steady state cases. And so for intensifying cases, you can see that the peak of the distribution of these convective bursts is located inside the radius of maximum winds. That's where the vorticity is higher. It also is a more, it's a location where the heating from the convection can more efficiently be transferred into an increase in the winds of the storm. So it's kind of a more favorable configuration for intensification. If you compare that for steady state cases, now look at the bars, you can see that the peak in that distribution is actually located outside the radius of maximum winds in a lower vorticity environment, less efficient for spin up. So that's a key difference that we've identified, statistically significant given our techniques, to distinguish intensifying versus steady state cases, just based on the radial distribution of convection. So that kind of idea has been adopted by the Hurricane Center and actually used in some of their displays. So this is a nice example, again, of ways that the Hurricane Center specialists can in real time look at some of the data that we transmit from the aircraft. This is a case of Hurricane Lane in the Central Pacific from 2018. So the shading here is showing you that the tail Doppler drive winds, I believe at 2-kilometer altitude. Actually, I think it's 0.5 kilometer, I'm sorry. So 500 meters showing you the tail Doppler drive wind speeds. So you can see the radius of maximum winds basically in this, approximately in this yellow circle. And then the white crosses here show you lightning flashes as detected by a ground-based lightning network. Of course, we can also use the geostationary lightning mapper from the GOES satellite as well to get you this information. Anyway, in this case, you can see that there's a lot of lightning flashes inside. This is at the same time, basically, that the aircraft was in the storm. You can see a lot of lightning was inside the radius of maximum winds at the time that the aircraft was in the storm. So Hurricane Lane at this point, actually, and over the next 12 hours, it intensified an additional 15 knots to reach nearly Category 5 over that 12-hour period. So again, I think this provides promise as a potential indicator of short-term intensification. So if you just take a broader brush look at the sort of research activities we've been doing at HRD with IFEX data, if you just go back and look at all of our publications over that period, and you group them into the 3 different goals, forecasts, nowcasts, and processes, you can see, perhaps not surprisingly, that the significant majority of our publications address the processes, although we do have other papers also looking at forecasts and nowcasts. And then if you further subdivide each of the topics that basically each of the papers addressed into things like TC structure and intensity change, air-sea interaction, boundary layer, precipitation, turbulence, microphysics, and so forth, you can see that most of the publications have focused on structure as well as boundary layer and precipitation processes. And really, there's been a comparative lack of focus on things like turbulence, microphysics, and the environment. So that suggests a possible gap in the research that we might want to try to address going forward. So what's the future of IFEX? Well, a key challenge, I talked about it a little bit before, is improving rapid intensification. That's really kind of the nightmare scenario for forecasters if you have a tropical cyclone just parked right offshore, maybe 24 hours from landfall, that undergoes RI. If we don't predict that, that can lead to really catastrophic consequences. Another important goal is to improve our guidance for pre-formation disturbances. The Hurricane Center has moved to 7-day forecasts. So as a result, that requires them to basically, often they'll have to issue what we call potential tropical cyclone advisories. So if we think there's a chance of a tropical cyclone forming, they start advisories. And so we need to better understand and predict basically the genesis of these systems as well. And then really, I think we want to get beyond just to focus on intensity. We really need to focus on improving our hazard guidance in general, and that includes things like storm surge, severe weather, rainfall, extreme winds. And really that requires, I think, a greater research emphasis on microphysics and turbulence and wind structure. So just as an example for the rapid intensification, so this is an error plot similar to what I was showing you at the start of this talk. But now if you look across lead times, you look for events from 2015 to 2017. You look at I believe these are the official forecast errors from the Hurricane Center. So if you break them down into cases that did not undergo rapid intensification versus cases that did undergo rapid intensification, so the black line is the non-RI events, and then the red line is the RI events. You can see a significantly greater error for cases that underwent RI. For example, at the 48-hour lead time, the error was basically 3 times worse than what we got for non-RI. So clearly RI is a huge forecast challenge and of huge forecast importance. So that's one reason that we're also moving toward that. And then coming back to the whole value chain idea, I think where we want to go with IFEX in the future. So, I showed this at the beginning, but really what we want to do now is we want to change or enhance our research efforts toward improving the forecast, not just of minimum pressure, TC position and peak winds, but also the wind structure as a whole, in particular the outer core wind field, microphysics, and turbulence. So that gets at some of the gaps in our research that we've had in identifying our publications. And so IFEX, again, primarily focused on aircraft data, will serve toward or be directed toward trying to improve the forecast of all 6 of those types of parameters. And then ultimately that would lead toward an improved hazard forecast, particularly with respect to storm surge and rainfall, wind gusts, and severe weather. And so, the hope is that by kind of broadening our focus of IFEX efforts, that will ultimately lead to even greater improvements in our forecast, not just in terms of the sensible weather, but also the hazards and then the downstream, looking toward a value chain perspective. So I think it's a really nice way to think of how IFEX fits into this overall concept. And with that, I'll just say thank you. I'll stop presenting.
Thank you, Rob. It's impressive the assets that you have to observe these storms to start with. Yeah, and you also very nicely put it, illustrated how the observations can directly inform forecasters to improve forecasts. So not only by assimilating them, but directly feeding into the sort of the forecast process that is being done by a human being. So I have an eye on the time. So we need to cut your questions a bit short. I'd like to ask Martin to give you one question that he has selected from the chat, and then you can possibly answer other questions in the chat.
Okay.
So one question that came in from a user just called C. Can you say something about how improved information about intensity improves or changes warnings or decision making? More specifically, how long before landfall is any change in intensity information necessary to improve or change evacuation decision making?
Yeah, so one of the sort of the key time period that I've heard, at least in talking with people, for example, at the Hurricane Center, is that 72-hour period. That's kind of the time that people need to make decisions on, when to start preparing, whether it's evacuating or moving ships out to sea or so forth. So that's really, like, in terms of the storm surge modeling and the storm surge warnings, I think their focus is on about the 3-day time period that they want to be able to lock in or have a good sense as to what areas are going to be most impacted by something like a surge event. So in terms of the intensity, I think the intensity is important for surge, but it's beyond that too. Of course, it's the wind field as a whole, as well as things like the motion, the trajectory of the storm, and the geometry of the coastline. But I think 3 days is probably about what people want, at least for something like a surge event, at least.
Okay, thanks.
Mm-hmm.
Yeah. Thank you very much, Rob. We take it to the other side of the Atlantic and to tropical Africa. Peter, the stage is yours. Please go ahead.
Okay, thank you very much, Michael. I hope you can see my slides.
Yes.
Yeah, so let's move to a place of the world where I think we are still a fair throw away from the perfect warning chain. So we're still, I think, struggling with the very first mountain there, and that's tropical Africa. Before I start, I should acknowledge Waves to Weather, the Waves to Weather project that funded most of the research I'm going to present. And of course, various people have contributed to what I'm going to show, so I'll mention those along the way rather than here on the title slide. So I'm going to address 3 central questions in this talk. So why care about African rainfall? How good are current forecasts, and how to improve them in the future? So I care about African rainfall. So this region is frequently subject to flooding. On the photograph there, you can see a picture from Ouagadougou in Burkina Faso in September 2009, when pretty much the entire city was 1 meter or so underwater, with substantial impact on the population. In addition, of course, there's a large dependence on rain-fed agriculture. So not only the extreme rainfall, but also the more ordinary rainfall is very important for people, and there's not much in terms of irrigation systems in the place. So if we had skillful precipitations on the, say, 1 to 5 day timescale, we could certainly improve hazard prevention and food production, but also there would be benefits for things like hydropower energy production, which is important across the region, water resource management, disease prevention, road safety, and so on and so forth. There's lots of good socioeconomic reasons to look into this problem. So how good are current forecasts? In the framework of Waves to Weather, we recently published 2 papers, both led by my PhD student Peter Vogel. So the 2018 ones was more specific on northern tropical Africa, whereas the 2020 one that just came out is kind of expanding the type of analyses to the entire global tropical belt. So let's look at rainfall occurrence first. This is defined by a simple 0.2 millimeter threshold. This is ISMWF 1 day, so 24-hour forecast, and this is the raw ensemble. And we're comparing the direct model output here to what we call a probabilistic climatology based on TRIM. So pretty much we take observations from the TRIM period and then a few days plus minus around the day of interest to build a PDF of rainfall. And then we use this as a kind of ensemble prediction. And what you can see is the picture is very red. So lots of areas with negative skill, particularly the drier parts of the oceans, mountain areas like the Andes, and also relatively large parts of Africa. So there's substantial problems with the model here to distinguish between a rainy and a non-rainy day, even in an ensemble sense. If we move on to amount, the map gets a little less red. If I switch back and forth, you still have the dry areas of the oceans and the mountains, but now you can see there's really significant problems over entire tropical Africa to the west of the East African highlands. This is now measured, I should say, by the continuous ranked probability skill score, so evaluating the entire ensemble distribution. So in this paper, we applied statistical post-processing to correct for some of the biases and dispersion errors we find. And again, I can toggle back and forth, and you can see there's improvement pretty much everywhere, and the red colors disappear. But tropical Africa in particular remains white on this map, and that means as it stands from a global ensemble prediction system at the moment, we cannot provide a model forecast, the one-day model forecast, better than a simple climatology to the hundreds of millions of people who live within this ellipse on the map. And I think for a meteorological community, that's an almost embarrassing result, I find. When we look at extremes, so potentially high impact weather, here defined by a threshold of 20 millimeters per day, again, 1 day ISMWF raw ensemble, we see a fairly similar picture of a lot of negative skill over tropical Africa. And you can post-process some of these problems away, but still you can see the map is essentially white. So no real skill in the model here at all. And you can also see that Africa stands in stark contrast to places like India or tropical Australia, where we have much better skill. So what can we do? And this is an overall pretty disappointing result. And I think the usual candidates are better observations. I mean, that's one of the themes of this webinar. but also there's questions of better data assimilation or just higher model resolution. So far, there's very few regional models in Africa with high resolution, better model physics, or even statistical prediction methods that take into account observations to train those models. So I will quickly step through those 5 points to give some perspective on where we should be going. I assume several of you have seen maps like this. There's not a specific day. This is a random draw from the ECMWF data coverage page with respect to radiosondes, and you can see there's very, very little across most of tropical Africa there, and that's kind of representative. This is not an extreme day. So for this part of the world, we're really enormously reliant upon satellite information, but with relatively little ground truth. We also sometimes don't know how good these satellite information actually are. So as part of the DACIWA, the EU-funded DACIWA project, we ran a radiosonde campaign in West Africa in the summer of 2016. So during 6 weeks, we launched about 900 radiosondes from the stations shown in the map here. And in the aftermath, we ran data denial experiments with the ECMWF operational system. And on these maps here, you can see differences between the system with the radiosondes and without. Left-hand side is 925 hectopascal winds, and you can see, particularly over the western part here, there's a substantial overestimation of the monsoon flow, so the southerly monsoon flow by the ECMWF model that's corrected by the radiosondes. And you can see on the right-hand side that if you have too strong monsoon flow, you have too strong cold advection from the ocean, and therefore you create a statistically significant temperature bias, again, that's corrected here in the downstream area by the radiosondes. And this is the analysis, and of course you would hope that such changes had an impact on forecasts too. But if you look at the kind of evolution with lead time, the solid lines here is the runs with the radiosondes, so they start from an RMSE of 0, and the dashed ones are without the radiosondes. You can see the gap in the analysis, but it takes order, say, half a day or so for those two sets to catch up. So there's relatively little influence of the observations on forecast, suggesting that either the system is very chaotic or that there's still too large deficits in the model itself. And that's also to be found in rainfall. This is now the one-day rainfall forecast with the sondes on the left-hand side and without on the right-hand side. So this is the bias with respect to trim, I should also say. And again, I'll leave it for you to compare the two maps. There's not a super obvious improvement. At best, I think you see some improvement over the downstream Sahel here with the sondes, but it's not a very large impact here. So one of the things we hope for improvement is Aeolus, a satellite that was launched in 2018 with a Doppler LiDAR in space. And that closes an important gap in the observation system, because now we can, for the first time, observe winds in the tropics in cloud-free areas. And a PhD student of mine, Maurus Born, he has started analyzing data impact experiments by the ECMWF. And we found a relatively large impact on the African easterly jet. So we are still investigating this at the moment, and the hope is that through this mechanism, we can also find some improvement on rainfall predictions and other fields. Next candidate on the list is data assimilation. I'm not going to say very much about this, but I think it's well known that data assimilation systems in global models, they mainly use error structures typical for mid-latitudes. And this is just one of the reasons why typically we find a maximum in the analysis error in the tropics, as shown in this paper by Privi and Errico for temperature, but you can find such patterns for other fields as well. So again, as part of Waves to Weather, we have a new project that experiments with energy and entropy conserving data assimilation approaches specifically in the tropics in idealized experiments to see whether we can achieve some improvements through modifications in data assimilation. Next candidate now, higher resolution. Sometimes when you talk to people, it sounds as if as soon as you go beyond convective parameterization, all problems will just magically disappear. I don't think that's quite as easy. This is not a silver bullet, and I just show you one example here from a recent study by my postdoc, Gregor Pante. So on the left-hand side, you see the bias in ICON with convective parameterization at the operational resolution of 13 kilometers. You can see fairly large biases here over the Sahel and also over some coastal areas here of Africa. If you move to higher resolution and switch the convection scheme off, you can see, in fact, particularly over the Sahel, where we have very large organized convective storms that create a lot of problems with parameterizations, there is a clear improvement, but there's also some areas where storms are triggered by more local processes, land sea breeze or complicated boundary layer mechanisms where there's actually a deterioration of the model performance here. So it's not quite that simple. An interesting outcome from that same paper is that in the model with the parameterization, the red dots here, when you compare to radiosondes, there is quite a large moisture bias throughout the entire free troposphere. And we think this is because the parameterization tends to detrain way too much moisture into the atmosphere. When you go to explicit and enhance the rainfall efficiency, you have a much better match with the radiosondes, and we found in the paper that there are some positive impacts then also on long wave radiation, temperature, pressure, circulation, and so on. So these things are all very closely connected, and we have to kind of get the full package right to improve forecasts. So this leads to better model physics. I said switching the convection scheme off is one important step, but there's also a lot of problems with the boundary layer, for example. And I think to improve that, you really need field campaigns. You really have to go to the places, as we did during Dakiwa here, for example, in Benin, and set up a lot of instrumentation and collect very good data. And with that, you can produce things like we see on the right-hand side here. So a very detailed, quantitative, conceptual model of the different stages in the diurnal cycle, for example, of low-level boundary layer clouds. And this is where we are at the moment. I think in the future, we need high-resolution modeling experiments, ideally with data assimilation, to really find out why there is such a bad representation, for example, of these low clouds in many models. Right, the last point on my list is statistical prediction methods, and I think a lot of people say, oh, NWP has moved on, and has improved to a degree that these things, there's no place for such things in our world anymore today. And we found again in Waves to Weather this is not entirely true. So again, Peter Vogel, he played around with simple statistical models over the Sahel. So what we see here is a time series from July to September 2016. It's the probability of precipitation on the vertical axis. So the gray means the days when it actually rained. The black dots is the raw ensemble forecast from ISMWF. You see a lot of days with 100% rainfall probability, which then in the end, in some cases, did not verify. The red line is the climatological probability of precipitation. So that's kind of ranging about 50% rain every other day. And now the orange line is the dynamical model forecast, but statistically post-processed. And you can see how significant the improvement is from the black to the orange here. And then the blue line is a statistical prediction model, so based on logistic regression. And that the only input this model is taking is rainfall observations from the previous day. So there's no model in here at all. This is pure statistics, and you can see that the performance is actually surprisingly good, because in Africa there are these coherent rainfall systems that propagate over several days, or African easterly wave disturbances that propagate. So if you compare the two on the map, so this is now the statistical model compared to the climatology, you can see improvement everywhere, or neutral results. So that's good. That means there is actually an added value compared to the static climatology. If you compare to the post-process, you can see that in the wet part of West Africa, where we have a lot of propagating systems, there is a substantial improvement here. So just by knowing where it rained the day before and the day before that, you can make a much better forecast than even a post-process dynamical model. But in the outer tropics here, where rainfall is more episodic and where there's a stronger influence from the more predictable extratropics, the post-process dynamical model wins. So I should come to an end. I hope I could convince you that tropical Africa has an urgent need for better rainfall forecasts. Current operational products are pretty poor over most parts of the regions. Statistical post-processing can cure some of the problems, and I think we should do this operationally, not just kind of in a research project like this. If we could increase observations, that would be good for a lot of things, model development, verification, and so on. But the impact on forecast, for example, from radiosondes is not spectacular. Maybe new satellite missions have a little more promise here. We need to work on data assimilation. We need to move to convection permitting resolution as soon as possible, but this will not solve all the problems. We need to move on model physics. That's the hardest bit. We need good observations for this, and we also need, weather services that look more specifically into problems in the tropics. And last but not least, at least for the time being, there seems to be some promise in also building statistical prediction methods, at least as a complement for some parts of the tropics where other methods fail. Okay, that's all I have. Thank you very much. And I would, of course, be happy to answer any questions.
Peter, thank you very much for the very nice overview, particularly also how observations in several different venues can help to improve forecasts and predictions. I guess we have time for hopefully a couple of questions for you. Martin?
There's one question from Bob Goldhammer. How frequently do hailstorms occur in tropical Africa? Do you have any experience with that?
Yeah, good question. Over the lowlands, practically never ever, only over the highlands. So areas like Kenya or Ethiopia, I think they have occasional hailstorms, and then you get some damage for crops and so. But most of the, let's say, West African lowlands, for example, it's too warm for hail.
And maybe two other quick questions. The first one would be from Shira. Is the statistical prediction model grid point based, or are spatial coherence also taken into account?
No, this is grid point based. Pretty much what we do is for every grid point, we find another grid point that shows the highest correlations with the previous days and the day before this rainfall. And then we just fit a logistic regression model. So it's very, very simple, very, very basic. I mean, Peter Vogel programmed this, I think, in 2 weeks. But we are trying to refine this now with more predictors and more sophisticated statistical tools, and we're looking a little bit into spatial coherence of the models being trained as well. So I think there is definitely scope for even better forecast based on observations alone, but I think in the longer run we would like to combine observational and model generated predictors to maybe get the best of both worlds in the end.
Okay, last question from Manos. Do we have an idea of the relative contribution of large-scale dynamics like MGO, etc., versus local dynamics to how poor the forecasts are in this area?
Yeah, good question. So in those future models that we would like to train, we will of course take things like MGO into account. Over Africa, the impact of the MGO is not huge, not comparable to say the Indian Ocean, West Pacific. But for example, in the more equatorial regions, we know there's a large impact of Kelvin waves, for example. So I think these definitely need to be taken into account. Over the Sahel, we have the African easterly waves, which are more synoptic scale, which seem to be the most promising candidates for, well, in principle, dynamical models too, but they all have some problems with those. So we will see how far we can get with the statistical models taking those wave modes, including the MGO, into account.
Okay, thanks. There's a couple of more questions in the chat. Maybe you can have a look later.
Okay, thanks very much.
Thank you, Peter. And now on to our last presentation for today, and even the very last talk of the series of webinars by Linus Magnussen. Please go ahead.
Thank you, and thanks for the opportunity to present this study. And what I'm going to talk about today is how we can use case studies in severe weather evaluation. And this material is mainly based on an ECMWF technical memorandum I published last year. But to start with some background thoughts. And the first one is why do we do forecast evaluation in the first place? And one can see it as a two-folded problem, because at least working at the Forecasting Institute, we want to make evaluation in order to guide future forecast system development, so to find deficiencies in our current system. But the other part is to inform users about the capabilities of the current forecasting system. And these are two different aspects, and they share some evaluation metrics, but quite often one need to evaluate forecast in different ways for those different purposes. Then the other problem that I usually start with is because we want to use ensemble forecast as the main tool for prediction of high impact weather. But the problem is that a single probabilistic forecast for this type of life-threatening events cannot be verified. So why do I make this statement? So first of all, we do not know the true probability distribution function at the forecast time. And in the end, we only get a single outcome. So we cannot verify the reliability aspect, like the ensemble spread, for a single forecast. The next one is that to overcome that, we need to have a large statistical sample to build on. But then the problem is that the life-threatening events are usually rare, and we often talk about return periods above 20 years, which means that if we want to look at the current forecasting system we have that we use for around a year before we do the next upgrade, we got a far too small sample to do a proper probabilistic verification. And then these type of life-threatening events are usually composites of sub-events, and they are unique in the horizontal and temporal scale. So you can think of it that we need a series of precipitation events during a longer period leading up to a major river flooding. And then for coastal flooding, it's usually a combination of waves, storm surge, tides, and the inland precipitation that ultimately give the flooding, and then the length and magnitude of heat waves. So instead, what can we do? So first of all, we can do a statistical verification, but lower our threshold to what we consider extreme in order to get a good sample size. Then we can also evaluate the model climatology. So how well can the model in a climatological sense capture the tails of the climate distribution? So do we have a frequency bias, for example? And then we can finally learn about important aspects from case studies that we can further dig into. That is what I'm going to highlight in this presentation. So in order to do this work, we have for a number of years now run a severe event catalog. And we have about 130 cases over the past 7-8 years. And the purpose for this is to collect material to do forecast evaluation, but also to look into new forecasting products, use them for further model experimentation, and also facilitate the communication on severe events to our users. And once every quarter, we use a case from this catalog for a newsletter article, and this starts to be a quite good library now. I think it's 25, 26 articles in a row in the HIWeather newsletters we put together about extreme events. So to show you what type of different aspects we can pick up from a case, I will use a recent example, which is the extratropical cyclone Alex that hit actually most part of Western Europe in the first days of October this year. So this is almost at midnight in the end of the 1st of October, where we had the cyclone center just off the coast of Brittany in France, and it had a stingjet-like feature in the backbending front with wind gusts reaching 50 meters per second. And then quite a far away from the cyclone center. So the cyclone center stayed over the Bay of Biscay up to the British Isles for a couple of days, but quite far away over the southern Alps, the same cyclone system caused very extreme rainfall, and one station actually observed more than 600 millimeters in 24 hours. And in the plot to the right, you can see the distribution of 24-hour precipitation or observations on that day. So on different timescales, what was governing this extremes? And we'll focus on the precipitation aspect. And on the plots here to the left, you see what we call the Extreme Forecast Index, which is a product we use at HIWeather to compare the ensemble distribution with the distribution of the climatology for each point and calculate an index to see how extreme it is. And if we start with the one-day forecast, verifying on the 2nd of October, to no surprise, we see very large values, close to 1 over the southwestern Alps. And I also included here the Extreme Forecast Index for the integrated water vapor flux, which indicates the transport of water vapor. And we see that we had a very strong moisture transport onto the Alps on this day. So if we go back 5 days before the event, we see the 2 plus to the bottom, and we see that the forecast picked up the broad scale risk of a wet day in Western Europe, but it's not so coming out so extreme over the Alps. And if we look at the moisture transport, we see that it's have a more westerly component instead of southwesterly that we saw in the 1-day forecast. And to look at the moisture transport, I also calculated the backward trajectories from HIWeather analysis for trajectories ending up on the 2nd of October, close to the French-Italian Mediterranean coast. And the coloring here is the specific humidity. And we see that the trajectories picked up most of the humidity over the Mediterranean, and that the fetch almost got the maximum length, starting from south of Spain and going towards France and Italy. So here the exact position of the cyclone leading to this transport seems to have been important. And even if we picked up the cyclone on the in the 5-day forecast, the exact position did that we missed the extreme, which we can see on the forecast evolution plot in the top left corner, where compared to the model climate in red, we predicted a wet day, but not outside the 99th percentile, and we see in the MPO that was far out. So if we look at the evaluation of the short range prediction and focusing on the Alps, we see that even if we inside this box over northern Italy predicted truly extreme, so the ensemble median was 130 millimeters, it was far from the average of all the observations inside the box, which was 230 millimeters. So factors that needs to be considered here is both the interaction with the orography and where the resolution plays a role. So here I included our HRES forecast with 9 kilometers and our control forecast with 18 kilometers. And we see that we get, for this short range forecast, this 1-day forecast, we get a little bit higher peaks in the rainfall. But another factor is during the fetch of these trajectories leading up to the event, whether we got the right evaporation and moistening of the air. So what we have done for quite a few of different type of extreme cases is then to try to list what are the important factors on different time scales. And for this type of flash floods in Europe, when you want to look into extended range, 2 to 4 weeks, we're talking about regime or this type of troughs over the Mediterranean area. And I put a question mark because we do not know yet whether these are predictable or not on this time scale. Then in the medium range, it's more about the exact position of the trough or cutoff low that determines the steering flow and the atmospheric rivers reaching towards the Alps. And then in the short range, the evaporation and the moisture advection and also precipitation processes in relation to orography. So by using this type of case studies, we then can come up with factors that we need to do a further evaluation on. And I'm discussing this more in the technical memorandum. So this then brings to the next step in the value chain. And I also included this picture with the different mountains. And from an evaluation perspective, we want to know how the value of the information propagates downstream, going from our precipitation forecast, and then how to modulate hazards, like in this case, a flash flood product from the Copernicus Emergency Service, and then leading into a warning. And then is the tricky point, how to verify the impact and how to use that information. So to finishing off with this, what we want to know then from this evaluation is which forecast range is most useful for this high weather forecast application, and how is the forecast information used, and how can we improve our forecast system. I'll stop there and take questions.
Okay, Linus, thank you very much. We have time for a few questions for you, I guess. So, Martin, what's going on in the chat?
Not a lot of questions for Linus so far.
Maybe then
go ahead.
Maybe let me go ahead and ask one. Well, it's curious. So, for example, if you look at the statistics of the ensemble, for example, now in your upper right-hand corner here, this distribution, this is the unstressed ensemble. So there's no post-processing applied to it. Is that correct?
Yes.
And if yes, do you know how the picture would change if you applied post-processing, particularly for, say, the orographic precipitation in Italy? Probably that the statistics would know that orography is still underrepresented.
So it's a good question. One type of post-processing where this NWF is to scale it down to represent point rainfall, to get the how is the distribution looking within this grid cell. But in this diagnostic, I have averaged over a number of grid cells, and the number of observations going into the average value is a couple of hundreds. So it's rather downscaling is upscaling, and it still points to an underestimation for this case. But we made a study a couple of years ago looking into the underestimation of orographic precipitation, and then afterwards a change in the moist physics went in, which made it better. So I don't have the exact answer in the top of my head how much we underestimate on average this type of precipitation events.
Okay, thank you, Linus. Martin?
No specific comment. Question. Brian Golding made the comment. I think that's always important to remind everyone that another reason for evaluation is to justify investment, of course. That's true for ECMWF, but I guess true for every weather service. And another comment that I wanted to make is that Linus is also involved into the new SARA high weather value chain project. So we're looking forward to get your expert opinion in that. There's one question coming in from Jimmy regarding forecast range for high impact weather. What decisions are needed locally? Yeah, what did you find in your evaluation well researched that what decisions were helpful locally, or is it from an ECMWF basis? Did you not go into local feedback?
I think that's where we really want to get information out from this value chain evaluation to see what type of decisions are happening based on the forecasts and on the different time ranges. And for example, if one have a type of decision 5 to 7 days ahead, that is a relatively cheap decision compared to the gain. So one have a low cost loss ratio, then one can add on a quite small probability. It's a small risk and still gain. So that's why even that one can have benefits in the medium range. But that's where I hope in the HIWeather project that we can get information more from the user side, which can help us in our evaluation.
And maybe a last question, Linda from the University of Reading asks, how are you defining useful in your final slide?
In our toolbox of metrics, I would probably look at the potential economical values, looking in for specific cost loss ratios to see how the whether the forecast has a positive economical value. That would be the first type of metric to look into.
Okay, thank you so much.
Okay, thank you, Martin, again for entertaining the questions. And with that, I would like to start coming to a close to the webinar. I would like to thank all the attendees for listening. I hope the presentations were of great interest to you and helpful for your own work. Thank you very much for everybody that participated by asking questions in the chat. And of course, last but not least, thank you very much to all of the speakers. Now imagine clapping hands and a cheering audience to give you proper credits. I would like to remind everybody about a HIWeather workshop taking place next week on the 3 days. Be reminded also on the HIWeather website, which unfortunately is not a net slide, but which is just hiweather.net. If you're interested in HIWeather, if you're interested in activities of the processes and predictability and process team, if you're interested to join and contribute, please get in contact. All the contact information you'll find on hiweather.net. And with that, thanks again, everybody. Have a good evening, a good rest of the day, a good night, wherever you may be. Bye.